Hi there, and welcome to this talk for the Bernoulli IMS One World Symposium 2020. My name is Bas Lodewijks. I'm a PhD student at the University of Bath, and I would like to use this opportunity to talk to you about maximal degrees in growing random networks in random environment, specifically for the preferential attachment model and the random recursive graph model. This talk is based on two papers that I've written jointly with my supervisor, Marcel Ortgiese. So let's dive straight in with the model definition. We start with some deterministic graph n0, and we will require n0 and m0 to be at least 1 for the preferential attachment model, and for the random recursive graph, we'll start with a single vertex and no edges. We then introduce the random environment as random vertex weights wi, which are non-negative, are IID and a sum law fw, and we assign the first n0 vertices the weights w1 through wn0. We then go from the graph Gn to Gn plus 1 by adding a vertex n plus 1 to the graph with vertex weight Wn plus 1, and by assigning it m half edges, and then conditional on Gn, we connect each half edge independently to some I in the graph Gn with a specific probability. For the preferential attachment model, that probability is Zni plus Wi divided by a normalizing term, where Zni is the in degree of vertex I in the graph Gn, and for the random recursive graph, this probability is Wi over a normalizing term. We can also allow for a random algebra, but I won't discuss this any further here. And visually, it looks like this. We start with a particular graph. We then introduce new vertices, which we then connect with specific probabilities to existing vertices, and we update their in degrees. Before we can talk about how the maximum degree in these graphs behave, we first need to talk a little bit about the random environment, and specifically how we can classify this into different groups that will yield different behavior. So the first class of vertex weight distributions is the bounded class, which consists of all distributions with a bounded support. Then there is the Gumbel class, which is closely related to the Gumbel maximum domain of attraction, and consists of all distributions in the Gumbel maximum domain of attraction that also have an unbounded support. And this implies that there exist sequences AN and BN such that the rescaled maximum converges in distribution to a Gumbel random variable lambda. And we can further subdivide this class into three subclasses based on the behavior of the sequence Bn. That is, there is a class SV, where Bn is L log n, where L is an increasingly slowly varying function. And there's the subclass RV, where Bn is asymptotically C times log n to the 1 over tau, for some constants C and n bigger than 0. And there is the class RAV, where Bn is e to the Bn star, where Bn star is as in the RV class with tau strictly larger than 1. And you can think of the SV class as the extension of the RV class with tau equal to infinity, and the RAV class as the extension of the RV class with tau equal to 0. And examples would be in the RV class, we can find the exponential distribution, the folded normal distribution, and the geometric distribution. And in the RAV class, we can find, for example, the log normal distribution. And then finally, there is the Fréchet class, which is exactly equal to the Fréchet maximum domain of attraction, which consists of all distributions such that their tail is a power law and that they have unbounded support. And if we set un to be the nth quantile of the distribution, then we know that the maximum vertex weight over un converges in distribution to a Fréchet random variable with exponent alpha minus 1. We also know that un grows roughly as n to the 1 over alpha minus 1, and we'll get back to that later. So with these classes, we can now properly talk about the behavior of the maximum degree in these two models. And we'll start with the preferential attachment model. We set theta m to be 1 plus the mean of the vertex weight distribution over m. And when the mean is finite, then we know that for any fixed vertex I, its in degree scaled by n to the 1 over theta m converges almost surely to some random variable xi I. And when we're in the Fréchet class with an exponent alpha in between 1 and 2, which means that the mean is now infinite, then we know that the in degree also converges almost surely, but even without rescaling. So how does this tie in with the maximum degree? Well, if we also define In to be the location of the maximum degree in the graph Gn, then when Fw is in the bounded class, or in the Gumbel class, or in the Fréchet class with an exponent alpha that is at least 1 plus theta m, then we see that IN converges almost surely to some random variable I, and the maximum degree also grows as n to the 1 over theta m, and converges almost surely to the supremum of the individual limits psi I. So we see here that the maximum degree is attained at some random vertex I for all but finitely many steps, and that also the maximum degree grows just as fast as the degree of any other fixed vertex. And this is behavior that is very similar to the original preferential attachment model without a random environment. So when do we see different behavior? Well, that is when we let Fw be in the Fréchet class with an exponent alpha that is less than 1 plus theta m. And if we then define pi to be a specific Poisson point process, then when alpha is in between 2 and 1 plus theta m, we see the following behavior. Here we now see that the location grows linearly in n, and when rescaled by n, it converges in distribution to b to the 1 over theta m, where b is some beta random variable. And the maximum degree now grows as un, and when rescaled converges to the maximum of a particular functional over this Poisson point process pi. So we now see that the maximum degree is no longer fixed, but keeps on growing to infinity, and the maximum degree now goes quicker than any fixed vertex degree. And this limit, this maximum over this Poisson point process, can be interpreted as follows. We can think of t as the moment the maximum degree vertex is introduced, and f as its vertex weight, and then the maximum degree needs to satisfy a balance between being born early, so t being small, and having a large vertex weight, so f being large. And finally, when alpha is in between 1 and 2, we see that both the location as well as the maximum degree grow linearly in n, and now the limits are a little bit more complicated, but for the maximum degree, you can think of this functional over this Poisson point process as the expected in degree. And again, this is a more complex balance, but we still want to satisfy a balance between being born early and having a large vertex weight. So what happens then when we look at the random recursive graph? Well, here we no longer have this preferential attachment mechanism, and therefore the much more subtle influence of the random environment can be seen much more clearly. So when we are in the bounded class, we now see that the maximum degree grows logarithmically, and when rescaled by log n, it converges almost surely to 1 over the log of theta m. And this is very similar to what we see for the random recursive tree and its multigraph counterpart without the random environment. Now, as soon as we allow for a distribution that has unbounded support, then we immediately see behavior that is different. So in the Gumbel class, when we look at the 3 subclasses, first for the SV class, we now see that the maximum degree grows like Bn times log n, which is ever so slightly faster than log n, and the location of the maximum grows with n, but grows slower than any polynomial in n. Then for the RV class, we again see that the maximum in degree grows as Bn times log n, but then times some constant prefactor, which depends on the value of tau, and the location of the maximum is roughly around n to the gamma. And then finally, for the RAV class, we see that IN grows almost linear, but only slightly slower, and the maximum degree now grows as Bn times log n over log Bn, and this log Bn correction comes from the fact that the maximum degree location is not linear, but just slightly slower. And then finally, when we are in the Fréchet class again, we can again define this same Poisson point process pi, and then when alpha is larger than 2, we see similar behavior as in the preferential attachment model, but now the limits are somewhat different. And most strikingly, we see that the limit of the maximum degree, when rescaled by un, is now a maximum over a functional over this Poisson point process, where the functional is now influenced by the time of introduction of the maximum vertex t in a logarithmic way rather than a polynomial way. And this really shows that when you take away this preferential attachment mechanism, that your degrees grow a lot slower, and that the influence of being born early is much smaller. And then finally, when alpha is in between 1 and 2, we see strikingly the exact same behavior as for the preferential attachment model. And this is due to the fact that in this regime, where the mean is infinite, then the influence of the random environment is much, much stronger than the preferential attachment mechanism. And therefore, the preferential attachment model basically behaves like a random recursive graph. It just ignores the presence of the in-degree in the attachment probabilities and behaves exactly or almost like a random recursive graph. So unfortunately, my time is up. There's no more that I can tell right now. But if you thought that this was very interesting, then make sure to check in during the Q&A session of the symposium, or to have a look at these two papers, the first of which is about the preferential attachment model in this random environment, and the second one is about the random recursive graph model. And they consist of what I've talked about today, but also things such as the degree distribution. And for the random recursive graph, we also study the second order behavior of the maximum degree for particular vertex weight classes, which is really cool too. So thank you very much for watching.